reminding me, because we missed a session from recording a week ago, and it is not available now for alert reviewing. Thank you again. So now we know what is IR drop compensation in control potential experiments, and also the sources of IR drop compensation. Conventionally, IR drop occurs mainly because of the resistance that is associated with the electrolyte solution. So that resistance is commonly called as solution resistance, but solution resistance, even though solution resistance is what contributes more than 90% to overall IR drop, there are also other resistance like from the interfaces I have just explained to you. So overall, the solution resistance added with other resistance from all the hetero interfaces we encounter in a given circuit can altogether form a resistance that is called uncompensated resistance. And that uncompensated resistance will always result in a drop in potential when we try to control the potential at the surface, interface. So that IR drop caused by uncompensated resistance has to be corrected in order to precisely, or in order to express the intrinsic activity of an electrocatalyst, particularly when we use control potential electrocatalysis. Voltammetric curves or responses in essence. Okay, so with that, we'll go to the common questions that has been asked by so many people to me via email, Facebook chat, Twitter messages, that should it be done with activity which is already normalized, or should it be done with should it be done before normalizing the activity? What uncompensated resistance value should be used? Whether we should take the uncompensated resistance value directly from the Nyquist plot, irrespective of whether it is normalized or non-normalized. And there are also people who asked me about the sources and factors that is influencing IR drop and its magnitude. And one of the major question was that what is the right way to perform IR drop compensation? In particular, the percentage of IR drop compensation. If you see the percentage of IR compensation in published literature, you would come around varying values from 80 to 95%, and it is also common to see 100% IR compensation. So which is correct? There 80 to 95% or 100%? How does it vary, and can these partial IR drop compensation serve the purpose for which we are intending to perform IR drop compensation? So these are the common questions that is commonly asked by people who were in connection with me and who wanted to get some clarification. So what I thought was that why don't we write a perspective on the same, so that it would be available for everyone for later reading. So I wrote, and I took a few specific examples where we can answer all these questions asked by the people who came in contact with me. So for the very first example, I took stainless steel electrode, which is a moderately active OER electrode. We all know that. And it is also having a very good charge sensor characteristics, because it always has lesser uncompensated resistance values than many electrodes that we use in electrocatalytic experiments. So this graph is what the Nyquist plot, and you can see two different labels at the X and Y axes. So where the superscript of Z indicates that this impedance value is normalized with the electrode's geometrical surface area. Okay, so this one, what we usually plot in all electrocatalytic experiments is the as acquired impedance value against the imaginary negative value of the imaginary impedance. So this is what we usually use, but this is the one which is normalized by the electrode area. Okay, so there are two questions you could have remembered from my first slides, but whether should it be done with the normalized activity or an activity that is occurred without normalization. You know what is normalization, right? So dividing the activity by the electrode area is called normalization in case of voltammetric responses. In the case of resistance, we are going to multiply it by the electrode area because of the relationship we derive from Ohm's law. So when you multiply the electrode area with the impedance, you will get normalized impedance. When you divide the current with the electrode area, you get the normalized activity. So now we have 4 situations such as this one. Either you can take the as occurred activity without normalization. Please note that the unit of current is just milliampere without any area in it. So you can correct it using the as occurred uncompensated resistance value. So this is after IR drop compensation. There is second case where you can normalize the activity by the geometrical area of the electrode. Then you can perform IR drop compensation with the as occurred uncompensated resistance. Okay. Here you get an unacceptable shape of LSV. This is not the shape we usually get. Okay. So this is an unacceptable shape. And there is third case. What we can do is that we can just take the as occurred activity and normalize, and correct it for IR drop compensation by taking as occurred RU. Then we can normalize it, and again we will have an activity that is normalized by area and also corrected for IR drop with an acceptable shape of LSV. Okay, and finally we have another situation. We can normalize both activity and both. We can normalize both activity and uncompensated resistance. Then we can perform IR drop compensation. So if you see, in all these 3 cases, you will have an acceptable shape of LSV after IR drop compensation and normalization. So if you look closely, what we can observe from it is that you should normalize the activity and the uncompensated resistance before performing IR drop, or else you can perform the IR drop with the as occurred activity and as occurred uncompensated resistance. Then you can normalize the activity. So this is how it should be done. Okay. So if you still have any questions, you can always ask me later. So in all 4 possibilities, you have 3 possibilities, which are going to result in an acceptable shape of LSV. By this way, you can ensure both 100% IR drop compensation, and also you can end up getting an acceptable shape of LSV. And there are these 2 things, right? Partial IR correction and complexities thereof. So it is not always possible to perform IR drop compensation 100% at all the times, even though we are going to use both normalized or both as occurred data of activity and uncompensated resistance. So here is an example of such an instance. This is the normalized Nyquist plot. As you can see here, this is an MOR curve of methanol oxidation reaction curve of a copper foam containing nickel impurities. As you can see, without IR drop compensation at this potential, so when we perform different percentage of IR drop compensation, you can see both are normalized. So the resistance is normalized and the activity is normalized. Even when we use both normalized activity and resistance, for IR drop compensation over 25%. Okay, so we are ending up getting an unaccepted shape of LSV. So this happens sometime when your catalyst is delivering high current density, but the resistance is even though smaller, you end up getting unacceptable shape of LSV. This is one of the examples where we encounter such a problem in IR drop compensation, particularly when we perform control potential experiments like LSV or chronometry. Okay, there are also cases where 100% IR compensation is still possible, but people somehow wanted to perform just partial IR drop compensation. An example is this: a nickel hydroxide electrode with normalized impedance as shown as an insert. You can see this is 100% IR compensation, and I have also plotted the partial IR drop compensation, 95%, 90%, and 75%. As you can see, the 90, 95% are almost the same. I don't know whether you can see, yeah, the 90, 95% are almost the same. So people often claim that, performing 90% would serve the purpose. But they forget one thing, that for why we are performing IR drop compensation. The first thing is that we want to show the intrinsic activity of the catalyst, which is free from IR drop. Second thing is that we want to use this LSV for TEFL analysis. So from theory, we know that for TEFL analysis, we need an over potential or potential scale, which is basically free from IR drop. So, which means it should be 100% free from IR drop. So, even though 90 to 95% of IR drop compensation can give you an activity which is very close to completely IR drop free activity, you cannot use this partially IR drop compensated LSV for TEFL analysis because it is not completely free from IR drop, which is forbidden by theory. Okay, that is why I always encourage people to perform 100% IR drop compensation. But again, I have already told you that there are cases when we cannot do such 100% IR drop compensation always. So, such as this one. So, what should we do in these cases is that either you can limit the potential window until you obtain an acceptable shape of an LSV for 100% IR compensation. Otherwise, you can perform controlled current experiments like chronopotentiometry or or sample current potential, sample potential potentiometry. So there are, I have not touched the sample potential potentiometry yet. So I'll discuss it in the next session. So there you can understand how we can avoid this particular problem and still will be able to extend the current range without any issue in IR drop, and still we can use the same for TEFL analysis. So these are the things for today's technical session. So in summary, when you want to perform IR drop correction, remember you should use either both as acquired activity and uncompensated resistance, or normalized activity with normalized resistance. Only these two can give you an acceptable shape of LSV. So if you perform the other way around, both will be incorrect. So that's all today. And I have forgotten to put the reference here, but you can always get it from my profile. The title of this paper is IR drop compensation in static electrocatalysis, but it will be corrected after proof correction as controlled potential electrocatalysis, because that is the most suitable title. So you can refer the paper after proof correction. Yes, with that, I would like to finish this, and I would like to share a set of PPT in which, just a moment, I'm sharing the questions that have been asked to me via various platforms. I'll start answering one by one. Then we can move on to the regular interaction session. Yes, these questions, I'm going to maintain the anonymity of the participant who asked the questions. So let's first start with the question I received earlier. So the filling on three things, the participant needed a clarification. First is the filling electrolyte. Why should be the molarity of KOH for HgHO? What should be the molarity of KOH for HgHO? Is it okay to fill it with 20% KOH? We frequently use it in 1 molar KOH electrolyte, or in this case 1 molar KOH will be better. Also, for Hg2SO4 electrode, I could not find a trustworthy reference regarding the molarity of K2SO4 filling the K2SO4 filling solution. Please help in this regards also. Yeah. So as you pointed out, when you use a reference electrode, in a solution of a particular concentration of KOH, you should always ensure that the concentration of the KOH solution inside the reference electrode to be the same. Because when we have different pH, we are basically forming a concentration cell. Because of the pH difference between the KOH in the reference electrode and the KOH in the cell, there will be concentration different, and that will lead to an interface formation. There will be a potential difference, and that will also affect your measurement. So always ensure that the same concentration of KOH is kept in both electrochemical cell and the reference electrode compartment. So as you know, 1 molar KOH, when you fill 1 molar KOH in the reference electrode, it will give you a standard potential at around 100 millivolt. To be specific, it will be 98 millivolt. But when you change the concentration of the KOH, it can vary from 98 to 110, 115. So you should always be careful about calibrating the reference electrode before you begin the experiment. About Hg2SO4 electrode, actually, if you look into the construction or the architecture of Hg2SO4, we have a platinum wire dipped into a liquid mercury, which is in contact with Hg2SO4, and which is also stacked up by crystals of K2SO4. Okay, so that crystals, those crystals of K2SO4 is what holding the electrode from not going into disintegration, which means that the K2SO4 crystal has to be stable in the solution. So when we can have such a stable crystal is that when we have a supersaturated solution. Okay, so we should always fill a saturated K2SO4 inside the Hg2SO4 electrode, because when the concentration of K2SO4 is very low, still there is possibility for the solvent, I mean, which is water in this case, has the ability to dissolve your K2SO4 crystal, which is basically holding your electrode. You can end up losing your reference electrode. So please fill K2SO4, saturated K2SO4 always. Yes. Is one day enough for the electrode to saturate in its filling solution? Of course, it is enough. If you don't, if you are not satisfied with that, you can always follow the OCP changes over a period of 24 hours. When you get a stable OCP, you can assume that your electrolyte, what you filled in the electrode compartment, reference electrode compartment, has reached an equilibrium between the electrode and the solution. So you can assume from there that your electrode is ready for analysis. Also, to check the reference electrodes, what I understood from our discussion is I should run HCR with PT working electrode and concerned reference electrode as counter. No. You should not use the concerned reference electrode as counter. You should use your concerned reference electrode as a reference electrode. Okay, because a reference electrode is ideally polarizable electrode, which means that we are not going to perform any reaction that can cause electron transfer at the reference electrode. And when you do that, obviously your potential of the reference electrode will change and you will never get your true potential value. What I said was that you keep the reference electrode as the reference electrode in the solution and take PT as the working electrode, and also you take another electrode as the auxiliary electrode, I mean counter electrode. Now perform HCR on the PT electrode. Now we all know that PT should always give an HCR onset of 0 volt versus RHC. Since you know the pH of your electrolyte, you can calculate, reverse calculate the potential of your reference electrode just by applying Nernst equation. So that's how it goes. So it is a very simple way. All that you need is you need a PT working electrode and a counter electrode, which can be anything, and the reference electrode whose potential you want to check. So by doing this simple experiment, you can easily calculate the potential, exact potential of your reference electrode. So that's all. Let's move on to the next question. I attended talks recently and was wondering why people chose alkaline media to show HCR. Can it be done in acidic media? Are there any restriction on that? And a slightly different one I wanted to was, okay, yeah. So for the second thing, you can always refer to my website where all the recorded sessions and the links are provided. And about HCR in alkali, it is not that we should not do HCR in acidic media. In fact, we can do HCR in acidic media, and it is very easy to perform HCR in acidic media because we have a lot of protons which are ready to be discharged and delivered as hydrogen. But the problem is that in acidic condition, there are not many catalysts which can be very stable to perform HCR under such harsh acidic condition. You know, even though some metal chalcogenides and metal phosphides which are recently reported are shown to be performing equally well to platinum, but because of their poor stability in the slightly anodic potential, there is no problem as long as you keep the potential scale in the reductive atmosphere. I mean, potential lesser than minus 0.5 versus 0.5 volt versus RHC. Most of the chalcogenides and phosphates are stable enough to carry out HCR, but upon prolonged operation, people have encountered the reduction of metal chalcogenides and metal phosphates to metals. So when those metals are formed at the surface, they tend to lose their electrocatalytic activity towards HCR. But the reason why people nowadays concentrating more on alkaline HCR is totally different, because in acidic water electrolyzer, the opposite reaction, I mean anodic oxygen evolution reaction, is catalyzed efficiently only by the materials which have iridium or ruthenium. Both are rarest metals, so they are not abundant, and they are also very, very expensive. So people have understood the difficulties in acidic electrolysis of water, and then moved on to alkaline medium, because in alkaline medium we have a number of catalysts that are stable enough to perform the energy intense OER with a very low over potential, such as nickel iron oxide hydroxide, with better onset and onset over potential and over potential at benchmark current density. I mean, better than IRO2 and RuO2. So in that case, all that you have to worry about is performing HAR in alkaline medium. Again, in alkaline medium, we don't have sufficient proton to be reduced instantaneously to deliver hydrogen. So what happens is that we should split water and take proton in order to perform HAR. That is why the state of the art platinum also struggles when it comes to alkaline HAR. It needs assistance from various other co-catalysts and electrolyte cations. So I'll talk about that in one of our upcoming sessions. So you could probably understand why hydrogen evolution reaction in alkali is very difficult and how can it be improved. So if you are more interested about alkaline HAR, you are welcome to read my recent review in current opinion in electrochemistry. And then I am from physics department. I know very little about both electrochemistry. Don't worry, continue to attend our LSEChem. And about good papers, you can start with the papers published by Bokris about the mechanism of HAR and OER in the 1980s. So that is a good starting point. And also parallelly, you should read some electrochemistry textbooks in order to understand the terms used in every characterization techniques. In particular, I would suggest you to read Electrochemical Methods, the Fundamentals and Application by Faulkner and Bod. So these are the things where you can start. So let's move on to next question. The value of 118 millivolt you were suggesting is a bit not clear to me. So in my understanding, are you saying that for HAR the potential value should be above minus 118 millivolt, as theoretical potential for HAR is 0 volt versus RHE, and on the other side for OER have to think in a similar way? Yes, because the value of 118 millivolt is derived from actually from Tafel equation, because we know that Tafel equation is nothing but it is constant plus 2.303 RT divided by alpha NF into log J. So this is what we know from IR drop free over potential, how it is correlated with the Tafel, I mean log of current density. Okay, so if you take this coefficient, I mean 2.303 RT divided by alpha NF. So in this we know that alpha is charge transfer coefficient, N is the number of electron transferred in the rate determining step, and F is the Faraday constant. Okay, so from the absolute rate theory of electron transfer proposed by Professor Marcus, who won a Nobel Prize for the same, believes that at any given time, at any given moment of time, there can be only one electron transfer. The electrons cannot be transferred, more than one electron cannot be transferred at the same time, and it is very highly improbable. So if there are any instances such as that one, more than one electron transfer, it is very, very improbable. Okay, so let's assume that all the rate determining steps in all the electrocatalytic reaction what we are studying are involving in transfer of only one electron. Okay, so if you solve out this coefficient, it will give you a value of 118 millivolt for n is equal to 1 is equal to 1. Okay, so this is the region where we still observe the BV characteristics, Butler-Bomber characteristic. If you move beyond this 118 millivolt, where the current contribution from the opposite reaction, if you take HAR, the opposite reaction is HOR, hydrogen oxidation reaction. If you take OER, the opposite reaction is ORR, right? So the opposite reaction and its current contribution to the reaction what we study should be less than 1% in order to satisfy the Tafel condition. So this can be achieved only when we move away from the reversible potential by 118 millivolt so that we will ensure that the current contribution from the opposite reaction is less than 1%, and we are truly in the TAFL region. So any TAFL slope that is calculated before this region or I can say is incorrect. Okay. So people reporting TAFL slope as low as 17, 13, 15, it is very common to see, and I don't understand how reviewers miss those things. I noticed that in all those reports, the region in which the TAFL slope was calculated is basically wrong. And in HCR, in which we have different mechanism, Volmer hierarchy and TAFL mechanism. The TAFL mechanism is the one which also accompanies a chemical part of reaction, in which there is electrochemical discharge of proton and then chemical delivery of hydrogen, which means that the chemical delivery of hydrogen is not usually the rate determining step. Instead, the electrochemical discharge of hydrogen. Even though only one electron is transferred during electrochemical discharge of hydrogen, the electrons that are involved during the chemical delivery of hydrogen is also have to be considered. That is why the TAFL mechanism following HCR electrocatalyst have lesser TAFL slope value than the one which are following more hierarchy mechanism. So what happens in this case was, even though the number of electron transferred in the electrochemical step is 1, the chemical step is adding up some more electrons. So overall, we are getting a lower value of TAFL slope. In those cases, when you are working with a catalyst which is known for performing the HCR electrocatalysis with TAFL mechanism, you can assume that your catalyst is involving in a reaction which is in which more than 3 or 4 electrons are transferred at the same time. So in that case, if you solve out the TAFL equation, you will get a value of I think for 3 electrons something around 35, and for 4 electron something around 27 millivolt. So you can keep your TAFL region above 50 millivolt cathodic from the reversible potential of HCR. So that would be sufficient for HCR. In the case when you use an electrocatalyst which is known for performing the reaction by TAFL mechanism. Of course, when you have a catalyst which is known for performing the HCR via Volmer hierarchy mechanism, always choose a region which is at least 118 millivolt more cathodic from the reversible potential of hydrogen evolution reaction. I hope I have made it clearer. Let's move on to the next questions. Next question, yeah, I have a question related to the electrocatalytic activity. How to define the electrocatalytic activity of an electrode in a half cell and a full cell. In a full cell, a lot of intermediates are formed during the electrochemical reaction. In addition, heterogeneous catalytic reaction are also can occur on the surface of the electrode. In such complex processes, how exactly can the electrocatalytic activity of the electrode be defined? Yes, that's a very good question, and your question has a lot of answers depending on the reaction you study and the probable number of and type of products that can be expected from the reaction. Let us take, for example, the simple water electrolysis. In water electrolysis, when you study the whole process in a full cell, the reaction that are occurring at the cathode and the anode are hydrogen evolution reaction and oxygen evolution reaction, and mostly 99.9% the product that are formed in water electrolysis is hydrogen and oxygen. So other products that can be encountered in a very less proportion are hydrogen peroxide and ozone in the anodic compartment, but definitely not in the cathodic compartment, unless otherwise you have other reducible or oxidizable impurities in your electrolyte, such as dissolved oxygen or some trace organic impurities. But it is you who should ensure there is no dissolved oxygen and there is no organic impurities by choosing deionized water and what we call millipore water, right, with high resistance value. So in those cases, the chances of having trace organic impurities and is very low. By purging the electrolyte with an inert gas like nitrogen or argon, you can also ensure that the dissolved oxygens are expelled well before you perform the experiment. Let's now come on to the electrocatalytic activity determination. So in electrocatalysis, what we do is that we perform either a voltammetric experiment or a potentiometric experiment, and we see the characteristic of an interface in terms of current against potential at time, or in terms of potential against current or time. So this is what we actually do. So when we say potential current, these two things can only be associated with the electrochemical reaction that is occurring at the interface, not the heterogeneous chemical catalytic reaction that is happening at the electrode surface. But of course, when we have such heterogeneous chemical catalytic reaction at the interface, that can block some electrochemically active sites and can lower the rate of the reaction. I mean, the rate of the electrochemical reaction occurring. All these can also influence the current or the potential what we are looking at in the monitor of an electrochemical workstation. So, in essence, what I'm trying to say is that any current or potential what we see from a voltammetric response or a potentiometric response is basically from the electrochemical reaction that is occurring at the interface. So any activity that is determined using this current or potential should only be of the electrochemical reaction that is occurring. If you are interested more in studying the heterogeneous reaction that is also occurring along with the electrochemical reaction what we are studying, you can always use highly sophisticated instruments like inline differential electrochemical micro differential electrochemical mass spectrometry and GCMS. So in those cases, you can quantify the products that are resulting from other heterogeneous catalytic reactions. So this is how we can identify the products from other processes. So in such cases, I would also like to answer your first part, the half cell reaction and full cell reaction. In half cell, what we usually do is that we exclude the current contribution from the counter electrode by placing a third electrode, which is nothing but a reference electrode, so that by sensing the potential difference between only the reference electrode and working electrode, we eliminate the current from the counter electrode and we only look into the current that is passing across the working electrode interface. So in that way, any current potential that is obtained in a 3 electrode cell can be considered as, not can be considered, it should be considered as the activity of an off cell reaction. But when you have a full cell study where you don't have any reference electrode, there will be a counter electrode and a working electrode. Your counter electrode is also going to act as a quasi reference electrode on which an opposite reaction is going to occur. Because of that opposite reaction, during the process of electrolysis, the potential of the counter electrode will also change, and depending on the changing potential of the counter electrode, your potential at the working electrode will also be controlled by the electrochemical workstation. So if you just measure the current of either one of this electrode, you are actually giving the overall performance of the cell, not only the half cell, okay, including the counter electrodes reaction. So that's how we do it in electrochemistry. Yes, that's all today from the questions, and I would like to stop here. And if you have any questions, you can always raise your hands, and Mr. Subhash will make you a host. Then you can ask your questions. Yeah, let me check the chat box. It's from Andrew. Kindly explain the initial experiments to perform to ascertain the suitability of an electrocatalyst material for either HR or OER or both. So it is nothing. All that you have to do is that take the solution of your interest, either acid or alkali, and perform rapid LSV or CV. You will roughly get an idea about the activity of your electrocatalyst. When you see some good activity in the first run of LSV or CV, also perform some 100 to 200 cycles of CV, then you can see whether the activity what you are observing in the first cycle is deteriorating rapidly or stable enough to be considered for further characterization using steady state method. So this is what you have to do. Make a electrode and run an LSV. So that's it. That is what basically you need to do. So there is nothing. But if you want to be smart to save resources and time, perform as much research as possible in the literature to know the trends and the properties that are governing the activity trends among various metals used in electrocatalysis. You will narrow everything down to 2 groups of metals. One is PD and RU for HR, and On the anodic side, it should be IRO2, ReO2, and nickel iron and cobalt iron catalyst. So these are the state of the art as of now. And if you are a material chemist and if you know something to play with the composition of this thing, because there is also recently the high entropy materials, you can give always a new catalyst, no matter how many times the same metal has been already reported. So you can play as you wish. So that's what you have to do. So all that you need is to perform an LSV and see whether the activity is deteriorating rapidly or not upon prolonging cycles of CV. So when you see a stable activity after under 200 cycles of CV, you can assume that your catalyst is qualified to be screened with the advanced electroanalytical techniques. Yes. Yeah. This is from Blessing. How long will a field last in research? Some fields where either disappear or another field takes over it. How do we cope up with the future fields? Okay. So if you consider my field of expertise, I mean the water electrolysis, it is not new. Actually, it has been there ever since the electrochemistry concept was invented. So people know that when you collect two graphite electrode with a battery and put it in water, you will see the formation of hydrogen and oxygen. So ever since that, people have been studying water electrolysis, and it is the recent interest that we are more concerned about our environment now because of the pollution and other things, and we want to rely on hydrogen more than on carbonaceous fuels. But the best way to produce hydrogen now is the steam reforming, which is again going to cause increase in CO2 emission. So the water electrolysis has gained high importance recently. But the problem with water electrolysis is huge energy consumption, particularly as the over potential that are associated with oxygen evolution reactions, right? So now people are looking into materials and tailoring the materials at the nano scale and engineering its electronic properties and adsorption, free energy adsorption characteristics in order to have a catalyst which can perform these reactions with very low input energy, so that we can save the amount of energy lost during this process. It is not only about the amount of energy lost, it is also about the longevity of the catalyst, because it is not the energy we are lacking, because we know that particularly in our country we have sun all around the year, and we can have as much as electricity possible from PV photovoltaics. So that electricity can be directed into an electrolyzer of stable electrocatalyst. Okay, when you don't have a stable electrocatalyst, you have to change the electrodes more frequently. That will hinder the continuous production of bulk production of hydrogen. So now the focus is to have stable and highly active electrodes in order to ensure the mass production of green hydrogen by combining photovoltaics with water electrolysis. So if you want to know the change, or if you want me to predict or forecast the future changes, water electrolysis is now slowly turning away towards beyond hydrogen generation. I would say it is not only for hydrogen generation. People now focus on hydrogen peroxide synthesis by tuning the anode catalyst to be highly selective for 2 electron water oxidation instead of 4 electron water oxidation. And also in the cathodic side, we all know that after the Walmer step, the intermediate what we have is a metal hydride or catalytic site with adsorbed hydride hydrogen add atom. So this hydrogen add atom is highly reductive, and it is a important hydride intermediate. So this can be used for the reduction of various organic molecules, and that can be done without using any metal hydrides. How beautiful is that? Just imagine, because metal hydrides, we know, they leave out metal cations as waste, and it is also very difficult to keep them stable in ambient condition because of their high reactivity. But in HCR, just by tuning the electrocatalyst structure, you can use the intermediate hydride for performing all these hydride mediated reductions in organic transformations. So this is how it is going to change in the future. And also the anodic reaction, where the oxo and superoxo hydroperoxide intermediates are formed in OER are being used for the epoxidation of alkenes and alkynes, and also controlled oxidation of alcohols to aldehydes and carboxylate acids and carboxylate esters. So esters and carboxylate esters. So this is how it is transforming. By doing this, they can also generate hydrogen on the opposite side. So it is not only about hydrogen generation now, it is about the various possibilities we can have with water electrolysis. So the key here is that always look for something which is not done yet. So that is what will change with this field. But the basic idea of water electrolysis will remain for centuries to come. So you don't have to worry about if you are in this field of water electrolysis. Yes, Dr. Dhanasekaran, if you are a host, you can unmute, you can ask your question.
Yeah, good evening to all.
Yeah.
And my question is, from the impedance spectroscopy, we can get the resistance value, right? Yeah. From that, we can use 2 electrode or 3 electrode system. For 3 it's supposed to 3 electrode system means that also that current current drop, it can be happened. So which one is good, 2 electrode system or 3 electrode system? First question this is.
Yes. I'll ask your first question. In electrocatalysis, what we usually do is that we want to characterize one catalyst for one reaction. I mean, for one half cell reaction, right? So when you want to do that, you should always determine the resistance associated with that half cell reaction. And in that case, you should always get your impedance plot, Nyquist plot, from 3 electrode system, because the uncompensated resistance, whatever you see in that impedance plot, will be the uncompensated resistance associated with only your catalyst, I mean your half cell. But when you want to take the impedance value from a full cell, that is the cumulative impedance or uncompensated resistance of both your counter reaction and working electrode reaction. So you cannot use this for normalizing the activity, for correcting the activity of half cell reaction, because the resistance what you see here is for the whole cell. So you can perform IR drop compensation for the whole cell polarization curve, full cell polarization curve, but which is not usually recommended because there is no meaning of doing it, because the main purpose for why we are performing full cell study is that we want to show when we apply certain potential to this full cell, it drives this amount of current. So that is what practically is going to be happening. So it is meaningless to show the IR drop corrected current in full cell. So IR drop correction is basically for two things: to show the intrinsic activity of your catalyst. So when we talk about the intrinsic activity of your catalyst, it is always the half cell. Okay, so you have to take the impedance value from 3 electrode system. And second thing is that you want to use this voltammetric response for TEFL analysis. So TEFL analysis, we do it for the half cell reaction, not the full cell. You know that TEFL analysis can only be done for one reaction, one part of the whole redox reaction. Yeah. So in that case, you should always use the impedance or uncompensated resistance from the 3 electrode system.
Okay.
Yes.
The next question is, so while doing impedance, we are using some substrate is some area, right? Whether this current after how I exactly say means that area anything affected by the that IR drop compensation. Normally we are getting from resistance only, but here we are using that area also. That area we can multiply it by the potential or current anything.
No. We don't have to multiply the current or potential. For normalizing the impedance, what you have to do is that you have to multiply the uncompensated resistance with the area. So it will give you the resistivity, I would say, because resistivity is nothing but the resistance of an electrode of an unit area, usually 1 centimeter square. So this resistivity has to be used for normalizing the correcting the IR drop compensation of a normalized activity, like I said. So that doesn't basically alter your potential or current. What it does is that it gives you the resistance value of your electrode with an area of 1 centimeter square. That's all. So it does not basically affect the potential or current.
Okay, okay. So no, so we need not worry about that surface
No,
area. I mean, the area.
electrode area. Yeah, yeah. You don't have
Electrode.
to. Yeah, because you have
Okay, okay,
used it to do, normalize the resistance. You don't have to worry about it.
okay. Sometimes it is giving very higher. I mean, resistance value nearby 40 ohm. Um,
Yes.
so that
Yeah,
I'm again some
yeah, yeah.
for your places you showed that before. That is for nickel
Mm,
something nickel hydroxide electrode. That
mm,
impedance it's showing only for 2 3 something.
mm.
But
Yes.
in my cases, whether it is
Yeah,
based on different
yeah.
experiment,
Substrate
but my
electrode.
cases, mm, mm.
Yeah, yeah. It is because of the substrate electrode you use. I used titanium foil as the substrate electrode in that case. Titanium foil has wonderful conductivity, so there is no issue of high resistance. If you use some other substrate like graphite rod or
Yeah, I'm using that nickel foam only.
oh, it
Nickel
should
foam
not
is
be then.
also
Then it should not be that much high. If you have used nickel foam without etching the surface with the acid, you may have resistance as high as 10 ohms, but 40 ohms is still very high. You could have altered the electrocatalyst ink composition. So, and you can
okay,
also try reducing the loading. Okay, sometimes when you
okay,
load more catalyst, the thickness of the catalyst will also impart huge resistance. So you can try
okay,
reducing the loading, and then you can again obtain the impedance value, or resistance value. Or there is no such streamlined data for loading dependent uncompensated
mm,
resistance
mm.
for any
Yeah,
catalyst.
I
So
understand.
yeah, if you are performing some experiments now, I would recommend you to study the loading dependent uncompensated resistance value and how it does affect the electrocatalytic activity. That would be a very good part of your paper to
Okay,
read. Yeah,
okay.
yeah,
Thank you.
yeah. And in the chat box, we have Claudel. Please, what is the explanation? Please, what is the explanation when in CV we just observe the oxidation peak without reduction, or the process isn't irreversible? Yeah. So I think you're here for the first time, I guess. So we have talked about this in the first and second session, and I really don't mind repeating it. So it is because of two things. Actually, there are three possibilities. The first is that, as you said, the reaction is completely irreversible. And the second thing is that the product whichever formed because of the oxidation or reduction is not available for the opposite reaction. When it happens is that when the product escapes the solution, particularly this is what witnessed, particularly when the product is usually a gas, because it will escape out the solution and it will not be available for the reversible reaction. And the third possibility is that your product which is formed by the electrochemical reduction or oxidation is converted into some other product chemically at the interface, like we encountered a question from a participant that there could also be a heterogeneous catalytic reaction to a different product which does not have the reversible potential of reduction or oxidation within the potential window what we are studying. So these are the three possibilities for not observing the backward reaction, okay, or the opposite peak for the opposite reaction. Yes, I think I have answered that question. And then Venkatesan Sanmuganathan, yes, what is the best cost-effective catalyst for a highly efficient HER and OER? Yes, that is the question I have also been trying to answer in the past 8 years. And now people are not worried about the cost. Now people are worried much about the stability and the longevity of the catalyst. Because even though platinum, ruthenium, iridium, all these are rarest metals of all the elements in the periodic table, we still have a lot of material in hand to be used in water electrolysis to produce hydrogen. Now the thing is that how to make them stable. Stable enough over period of months, several months, so that will not be asked to uh, change the electrode assembly more frequently during the process of green hydrogen generation. If you are more concerned about the cost-effective catalyst, I would suggest you to avoid touching platinum, ruthenium, iridium, and rhodium. So if you are not touching these four metals, you can always have other catalyst, and they can also be effective. I mean, catalytically active. For like for example, uh, the spinels which contain nickel, cobalt, and iron, and there is also perovskites which contain all these metal oxides with rare earth elements, and also there is oxide hydroxide and layer double hydroxide for OER in alkaline condition, and for alkaline HER we have metal hydroxide, metal chalcogenates, and metal phosphates with the triple of platinum and ruthenium, not in bulk amount. I mean 1 to 2.8% of platinum and ruthenium with metal hydroxide as co-catalyst, and there is also mixed metal phosphates which can perform this reaction in both acid and alkali very well for HCr. So when you are worried about the cost, you should not touch platinum, ruthenium, iridium, and rhodium. So these four metals should be out of your table. Then you can play with all the other metals that are already known for electrocatalytic activity. Yes.
So what about silver, sir?
Yeah, silver is not a good catalyst for both OER and HCr. If you look into that, is mainly because of its strong hydrogen and oxygen absorption characteristics. In electrocatalysis of any reaction, what we should look into is that we should always see where does that metal lie in the Sabatier volcano plot. You know, the Sabatier principle suggests that the absorption energy of the intermediate should neither be too strong or not to be too weak. So when these two are the case, when the intermediates are having strong absorption with the catalytic side, it will poison the surface. Or in other words, after forming the hydroperoxide intermediate for oxygen evolution reaction, and after forming the metal hydride intermediates for hydrogen evolution reaction, it will require more amount of energy to release them out because of its strong absorption characteristics. On the other hand, when you have weak absorption characteristics, so the formation of intermediate will itself become a problem. Okay, so all that we need is a moderate absorption free energy for the intermediates that are involved in any electrocatalytic reaction. If you take silver, silver is not a good electrocatalyst for both oxygen involving and hydrogen involving electrocatalytic reaction, but it is shown to be good with other co-catalysts for ORR and carbon dioxide reduction reaction, and in some cases for nitrogen reduction reaction. Those are mainly because of its poor hydrogen evolution reaction selectivity. So silver is not a good option to go for, particularly for HCr and OER. And yeah, Ms. Srividya, if you are a host now, you can unmute and ask your question.
Good evening, sir.
Yes.
Sir, I have a doubt about calculating the electrochemical surface area, because usually we will calculate ECSA from the ratio of CDL by CS, but you have been insisting that it is not really the right method, because the CS, the specific capacitance, we take it from reference. So recently for a project, sir, I'm starting to working in electrochemical sensing. So there also for in the ferricyanide medium in the PBS buffer. So there also like they are using a derivation of like they're using the Randall-Sevick equation. But fundamentally in Randall-Sevick equation, what we have is the electrode surface area, right? So how can we use that to get the electrochemical surface area? So and also when comparing like even the CDL by CS, this method is also similar to what I think it seems to be derivative of Randall-Sevick equation. So I have this question, but that they are taking this value from a reference where they have used I think a platinum electrode, but they have substituted only the electrodes area, and they have obtained that diffusion coefficient for ferrocerium complex, and then they are using that, but it won't give accurately, right? So in that cases, what could be the best method to get at least the nearest value in either cases, in both cases?
Yes, actually using Randall-Sevick equation is a good way when compared to the serial, because in serial, as I said earlier in one of our sessions, that what we are actually considering here is absorption desorption currents. okay, which is not basically involving any electron transfer. So basically not all the adsorption desorption site which contributes to CDL cannot be can be electrocatalytically active. Okay, so even though we are going to determine the specific capacitance on our own for our catalyst following the literature, still the surface area what we are going to get is electrochemical surface area, not electrocatalytically active surface area. Okay, so there is a difference between electrochemical surface area and electrocatalytically active surface area. So that is why I usually don't recommend people to use the electrochemical surface area obtained from CDL measurements. But on the other hand, when we use the Randall-Selznick equation, there we are actually following a redox reaction which is purely Faradaic, which means that there is an electron transfer. So that electron transfer actually indicates the number of sites where there is a transfer of electrons across the interfaces. So any area that is calculated using Randall-Selznick equation can actually attributed to be electrocatalytically active surface area. But again, there is an issue because this electron transfer rate and the kinetics depends on the reaction what we study. In Randall-Selznick equation, what people usually do is that they either take the ferroferry redox couple or the ruthenium 3 hexamen complex. So to study the redox property of that particular redox product, which are known for their complete reversibility and freely diffusing nature. I mean, they do not specifically get adsorbed to the electrode surface. So their CV structure is actually most suitable for Randall-Selznick analysis, because we know that the Randall-Selznick analysis can be applied only to those reactions which are completely Nernstian, right? So the IP-IC ratio is 1, the peak-to-peak separation is closer to 59, and the peak position does not shift with the increasing scan rate. All these three characteristics have to be met in order to qualify a reaction to be analyzed by Randall-Selznick equation. Okay, but since it is saying about the electron transfer, unlike the CDL, any area that we obtain from Randall-Selznick, from applying Randall-Selznick analysis, can be considered more closer to the actual electrocatalytic surface area. But as I said again, this area is calculated for a different reaction than what we are intending to study. For instance, in the case of OER and HER, it is going to be a different reaction. For the sensor studies you are willing to study, it is going to be some other analyte which may interact with your electrocatalytic interface or the sensor platform in a completely quasi-reversible manner or non-Nernstian manner. So in that case, you cannot attribute the electrocatalytic active surface area determined from Randall-Selznick equation. So yeah, it is always impossible. It is always impossible to get an exact electrochemical surface area. But for what it's worth, for not having anything at all, we can go for Randall-Selznick equation. And when we don't have that option, we can go for CDL. So this is what we have currently. So there is no way in getting for getting an exact electrocatalytic active surface area, particularly for a multimetallic sensing platform or electrocatalytic system. So if you know the diffusion coefficient and if you know the concentration, exact concentration, and of course you can determine the area from Randall-Selznick equation.
Okay, sir. Thank you.
Yeah. We have a question from Sriram Prabha Ramasamy. The session, thank you very much. The session is fully informative. Sorry, I have missed the previous session. Can we get the previous record? Yes, you can always get the previous recorded sessions from my website. I usually share the recorded version and the link on social media tomorrow or day after tomorrow. And you cannot find the penultimate session, which we held a couple of weeks back because I forgot to record it. And today I'm recording it, so it will be available for viewing later. And then Dr. Dhanasekaran, what about PD? Is that efficient for OER? No, PD has strong hydrogen adsorption for HR and poor oxygen adsorption toward OER. So it is not qualified as per the Sabatier principle. But some people use PD for enhancing HR activity because of its favorable HR adsorption when compared to nickel. So if you take the platinum group metals, the nickel group metals, nickel, palladium, platinum, nickel has the strongest hydrogen adsorption, and then palladium, and then platinum. Platinum is the one metal which has the most optimal hydrogen absorption free energy. That is why this is the best catalyst for hydrogen evolution reaction. So when you go up the group in the periodic table, the hydrogen absorption free energy increases. So which means that the formation of stable metal hydride intermediate also increases with increasing hydrogen absorption free energy. But in as I said recently, for the question related related to what was asked by Mr. Joe Blessing, that when we have stronger absorption free energy towards hydrogen, which means that we are having stable metal hydride intermediates. These stable metal hydride intermediates can be used for organic transformation in a combined electrochemical and organic catalysis. So there are lots of possibility. So when you are worried about only improving the HR activity, palladium is not the option we should usually go for. So that's it. And we have one more question from Dr. Venkatesan Shanmuganathan. How do we measure the changes in over potential in a reversible system? It doesn't matter whether it is a reversible or quasi-reversible or irreversible system. The change in over potential can always be measured by performing chronopotentiometry. You set the current density and observe the change in potential over time. So that's how we do it. And if you want to do it with the voltammetric response, you can perform a number of cycles of CV or LSV in order to see how the over potential at a certain current density varies with increasing number of cycles. So these are two ways we can monitor the change in over potential. And in opposite, you can also do such study for observing the change in current density. So using chronoamperometry and voltammetric responses, transient voltammetric responses. Yes, I think I have answered the question. And thank you very much. Now we have exceeded the time of today's session. And thank you very much for joining me for another session of LSEChem. And I'm very much delighted to resume this session again for yet another week. And I would like to have this session uninterrupted for all the upcoming weeks. Please do join me and ask me any questions if you have. I would be very much delighted to be answering all your questions. And also, if there is something you wanted to share it with me, or if you have some conflicts of thoughts with the things I'm saying on this platform, you are welcome to express here so that I will also learn from you all. Yeah. With that, I thank you all one more time. See you all the next week. Bye-bye. If you're done, you can leave the room. Thank you.